Hi guys, Mohit here. This is part 1 of my CUDA Graph series. But before getting into CUDA Graphs, I first want to explain what a normal CPU to GPU execution looks like, because this makes it much easier to understand why CUDA Graphs are useful. Normally, your application is running on CPU. When it reaches an operation that needs to run on GPU, the CPU launches a kernel by queuing the GPU work into a CUDA stream. This kernel launch is generally asynchronous. This means the CPU doesn't have to wait for the kernels to finish. It can continue doing its own work and queue more GPU work. Within the same CUDA stream, the operations are ordered, meaning if the CPU queues the kernel ABC, the executions happen in that order, which is ABC. For example, if the queue is BCA, the execution happens as BCA. Now, every time we launch one of these kernels, there is a small CPU side submission work required for that kernel to the GPU. This gives us a small amount of kernel launch overhead for every individual launch that we do from CPU to GPU. For example, if we launch one large kernel that takes a lot of long time to run, the small overhead barely matters, right? But if we launch hundreds or thousands of small fast kernels, each has its own launch overhead. All of these small overheads added up together can eventually become a bottleneck. This basically is what we mean by kernel launch overhead. The problem isn't that the GPU kernels are slow. Basically, the problem is that repeatedly launching all these kernels one by one from CPU causes this. And the solution for this is basically CUDA graphs. So now we know the problem. Normally, the CPU has to submit these GPU operations one by one, and every kernel launch comes with a small amount of CPU overhead. Now, when we move to the CUDA graphs, instead of submitting the same sequence of GPU operations individually every single time, CUDA lets us capture that sequence of works into a graph. This graph contains the GPU operations we want to run along with the dependencies with them. Once we have this graph, we can replay the whole sequence again without the CPU having to submit every kernel individually like before. So the main benefit is that when we reduce the kernel overhead, which is especially useful when you have lots of small and fast kernels, it's important to understand that graphs don't actually make the kernels faster, right? The main optimization is how efficiently we submit the work on the GPU. That's it. That's all the main thing that we care about, on how efficiently we are submitting the kernels to the GPU. Now the main question is, how do we actually create one of these graphs? So there are two ways to create CUDA graphs. One is explicit graph construction, and another is stream capture. So with the explicit graph construction, we manually build the graph. We create the nodes, define the operations, and specify the dependencies between them. This gives us much more direct control over exactly how the graph is constructed, basically. And then the second approach is stream capture, which is more straightforward, meaning instead of manually building every node, CUDA watches the operations being submitted to the stream during the capture and uses those operations and the dependencies to build the graph for us. Where are these actually methods used compared to these applications that we use? In PyTorch, the normal torch.CUDA graph is used by stream capture, and in CUDA C++, either of those works properly. And frameworks like JAX and TensorFlow usually hide these low-level details. Their compiled execution systems can be command buffer or graph-like execution mechanisms internally. So as a normal users, we generally aren't manually choosing between CUDA explicit graph construction or stream capture, for example. Now that we know what CUDA graph is and how to create one, let's look at the basic life cycle of how the CUDA graphs actually are in stages. So this is the CUDA graph life cycle. So there are 3 steps, which is one, capture, and then you prepare, and then you replay it. So first is capture. During capture, CUDA records the sequence of GPU operations that we want to repeat. For example, let's say our workload has kernels A, B, C, and D. CUDA captures these operations along with the dependencies and creates a CUDA graph. So now the CUDA has a graph that describes what operations need to run and the order they depend on each other basically. Now the second stage is prepare. Prepare, once we have captured the graph, CUDA needs to prepare it for execution. CUDA takes these graphs we create and turns it into a ready to run version called a graph executable. You can simply think of it as for example, CUDA preparing the captured graph so that it can be launched efficiently again and again. And then the final step is replay, where instead of the CPU submitting the kernels A, B, C, and D individually every single time, the CPU can launch the prepared graph that we just created with a single graph launch. CUDA then executes the operation stored in that graph, and when we need to run the same workload again, we can simply replay the same prepared graph again and again. So the basic lifecycle is basically capture, prepare, and replay. There is a visualization here that I can show. Yeah, instead of launching every single time, which costs the same amount of time, same amount of workloads that it takes to launch a kernel, you launch it all together and then you calculate all, saving you much more time than before.